everybody, getting ready to do lesson 2.5 part 2 classwork today, pre-calculus math. If you need any course materials, email me here, animatedpowerpointmathvideo at AOL.com. Note-taking guides, homework sheets, classwork sheets, email me there for that. Today, 2.5 Fundamental Theorem of Algebra Part 2 classwork. We got 60 points here in classwork and 0 points in notebook taking today. Teachers, today's bell work is describe the graph of the function and identify the vertex of these quadratic. Students, give your students about 5-6 minutes for these. Okay, welcome back, students. Hopefully these are completed. Let's go over them now. For the first one here, x squared minus 7x minus 8. So to do this, we're going to complete the square here. 7 over 2 squared minus 81 over 4 here. And so when we have this here, this situation here, the parabola opening upward with a vertex, our a here is positive, so you know your parabola is going to point up like that. And then negative b over 2a, so it'll be 7 over 2 over 2a. See, negative b, parabola opening upward with a vertex, negative b, negative b over over 2a. So negative b over 2a here. That's our x, and then we plug our x back into here to find our y. We come up with 81 over 4, a negative 81 over 4. So it's 7 over 2, which is what, 3.5, which is about here. Then 81 over 4 is like way down here. It'd be like 20 and 1/4, negative 20 and 1/4. And so the thing goes like that, is what it does. So on this grid here, if you're going to use this grid, well, if you use a graphing calculator, you can find it. This grid here won't help out unless you rescale your values here on your grid. And then down here for this, well, I put it up there. Yeah, so this thing does go up like that. This is definitely an approximation of this parabola here. And then down here, for the second one, we have a negative. So the negative, you know, is going to go like this. It's going to bend down like that. There's an approximation there. I rescaled it here. That's how I got this parabola. Very much an approximation. So for the second one here, it'd be negative b over 2a would be your x-coordinate. So negative b over 2a. So it'd be this here. It'd be negative 1 over 2. This is vertex form of this quadratic here. So this would be your h, and then k would be here, 25 over 4. So parabola opening downward with vertex at 1/2, because it's the negative h. So this is 1/2 here. So it'd be 1/2 and 25 over 4. So when x equals 1/2, y equals 25 over 4, which would be up here somewhere. So it would be right there, it would be your vertex, and then your parabola approximately goes like that. So that's what you should come up with there. Describe it. Well, you could describe it by graphing it. And this is a description here, so that would work as well. Moving on now into our lesson, first page, conjugate pairs, example 3. Note that the two complex zeros are conjugates. That is, they are the forms a plus bi and a minus bi. So complex zeros occur in conjugate pairs. So f of x, let f of x be a polynomial function that has real coefficients. If a plus bi, where b cannot equal 0, is a 0 of the function, a plus bi, then the conjugate a minus bi is also a 0 of the function. Be sure you see that this result is true only when the polynomial function has real coefficients. So it has to have real coefficients. For instance, the result applies to the function f of x equals x squared plus 1, but not to the function g of x equals x minus I. It would not work here using conjugates to find your zeros. In this case, it would work. So if we get into an example of doing that, finding a polynomial with given zeros, find a fourth degree polynomial function with real coefficients that has -1 and -1 and 3i as 0. So it gives you these as your zeros. Because 3i is a 0 and the polynomial is stated to have real coefficients with real coefficients, you know that the conjugate -3i must also be a 0. So from the linear factorization theorem, f of x can be written as a times x plus 1, x minus 3i, x plus 3i. For simplicity, let a equals 1 to obtain x squared plus 2x plus 1, and then when you multiply these two together, you get x squared plus 9 is what you get for your final binomial there. So when you multiply these together here, you get x to the 4th power plus 2x cubed plus 10x squared plus 18x plus 9 when you multiply these together. Okay, let's try one now. Find a polynomial function, real coefficients, that has the given zeros. So we got 2, 2, and then 4 minus I. And, well, it says, warns you there are many correct answers. And then down here you have somewhat of the same thing here. So for the first one here, x minus 2 squared, since 2 is a 0 twice. And then we have x minus 4 minus I, and then x minus 4 plus I is how we would put this into a factor of this polynomial. And then when you multiply these together, we have x minus 2 squared, and then this, when you multiply these two together, you get x minus 8x plus 16 plus 1 here. You see, negative I squared would be 1. So, and then when you combine like terms here, you have this, when you expand this out, x squared minus 4x plus 4, and then x squared minus 8x plus 17 here. This should have been x squared. This should be a squared here. This should be x squared here. And then when you combine like terms here, or rather, we're not combining like terms yet. We're going to multiply these two together. So x squared times x squared, and then this expands out to this here, this fourth degree polynomial. So that is really what you should find here with these given zeros. And then down here, wait a minute, we're not done yet. Note that f of x equals ax to this thing here, where a is any non-zero real number, has zeros 2, 2, and 4 plus or minus I. So when you have a minus here, you know you have a 4 plus I as well. That's really the gist of this problem. Here, well, that's up to you. Let's move on to the next one here. Finding a polynomial with given zeros. So we have 2 and 1 minus I as zeros, and f of 1 equals 3. So in this situation here, because 1 minus I is a 0 of f, the conjugate must be 1 plus I. We have 1 minus I, you've got to have 1 plus I. Must also be a 0. So, and we have 2 here as a 0 as well. So a times x minus 2, then x minus 1 minus I, then x minus 1 plus I here. I mean, these will produce a 0. And then by multiplying these two together, a times x minus 2, and then x squared minus x times 1 plus I, then minus x times 1 minus I, plus 1 minus I squared. So we're multiplying here by grouping like terms together here. And then a times x minus 2 times, when you hash this out here, it becomes x squared minus 2x, so negative x times 1 plus negative ix minus, again, minus x, and then minus, or rather a positive ix, so those two would cancel out. And then plus 1 minus I squared. I squared is 1. Combine these two terms together and you get 2. So this all becomes x squared minus 2x plus 2. And then when we multiply these together, we get x cubed minus 4x squared plus 6x minus 4 times. To find the value of a, use the fact that f of 1 equals 3. So when we plug in 1 here to find a, it has to equal 3 here. We plug that in. We're going to solve for a now. Thus a would equal negative 3, and you can conclude that f of x equals negative 3 times this polynomial here. And so when you multiply this out here, you get negative 3x cubed plus 12x squared minus 18x plus 12. So that's kind of a nifty way to find a polynomial by providing given zeros. Let's try one now. So write the function a in completely factored form and b in the polynomial form. So we have a fourth degree polynomial. We have 1, negative 2, 2i as zeros, and then a solution point b f of negative 1 would equal. Okay, so our problem here is to write the function a in completely factored form and b in polynomial form. So we have a fourth degree polynomial. Here are our zeros at 1, negative 2, and 2i. And then we have a solution point here when x equals negative 1, y would equal 10. So by knowing that, we can come up with our zeros here. A, which we don't know yet, is x minus 1 for that one, then x plus 2 for this one, and then x minus 2, and then x plus 2i for 2i. And then when we multiply these together, we can simplify it down into this polynomial here, x minus 1, x plus 2, x squared plus 4. And we know that f of negative 1, this is negative 1, equals 10. So a here, does it equal 10? And it's like negative 2 times 1 times 5 would equal negative 10. It would not equal 10, but it would equal negative 10 here, f of negative 1 here. So this is what it equals when a equals negative 1. So we're going to stick this out in front anyway here. See negative 1, that'd be negative 2, and then negative 1 in here would be 1, and then negative 1 in here would be 1 plus 4 would be 5. So a times negative, that would be, so a would have to equal negative 1 in this case here. A would have to equal, because we know when we plug in x, so we get 10. So a equals negative 1. So we stick this out in front, and then we multiply through now on our array that we think that are zeros. And then what we get here, we get negative out in front of those other expressions, and then when you multiply these together, you get that, and you get this here, and when you multiply through, you come up with negative x to the fourth, negative x cubed, negative 2x squared, negative 4x plus 8. So that will be your polynomial with these conditions here. Page 7 of classwork, factoring a polynomial. The linear factorization theorem states you can write any nth degree polynomial as the product of n linear factors. So this would be your algebraic expression for this theorem here, a to the nth, x minus c1, x minus c2, x minus c3, x minus c to the nth. So this result, however, includes the possibility that some of the values of c to the I are complex. The following theorem states that even when you do not want to get involved with complex factors, you can still write f of x as the product of linear and or quadratic factors. So this is something to keep in mind that we're going to apply now our future work here. Factors of a polynomial. Every polynomial of degree n greater than 0 with real coefficients can be written as the product of linear and quadratic factors with real coefficients where the quadratic factors have no real zeros. So a quadratic factor with no real zero is said to be prime or irreducible over the reals. Be sure you see that this is not the same as being irreducible over the rational. So there's a difference between rational numbers and real numbers. Speaking broadly, it's getting very technical. For example, the quadratic x squared plus 1 can be written as x minus I, x plus I, is irreducible over the reals and therefore over the rationals. On the other hand, the quadratic x squared minus 2, when you write it like this, is irreducible over the rationals, but reducible over the reals. So by using real numbers here, you can reduce this back by using reals, but rationals, I mean the square root of 2 is not a rational number, it's an irrational number. So you're using an irrational number, but it is reducible over the reals. By just not including reals in this set, you can still reduce this. Okay, let's try an example here with all that technical information. Write the polynomial a as a product of factors that are irreducible over the rationals. So begin by factoring the polynomial into the product of two quadratic polynomials. So we have this expression here, and it would be x squared minus 5x squared plus 4. Both of these factors are irreducible over the rationals. So it's irreducible over rational if you kept rational numbers. B as a product of linear factors and quadratic factors that are irreducible over the reals. And B, by factoring over the reals, you have this again, and then we have square root of 5, x minus square root of 5, and then x squared plus 4. So by factoring over the reals, what a quadratic factor is irreducible over the reals. So these factors here are irreducible over the reals. So by using, again, irrational numbers, which are part of the set of real numbers, you can still factor this thing, because square root 5 is an irrational number, but we're going to use it anyways. It's not a rational number, but it is part of the real number set. So in completely factored form, so this would be, we're going to use complex numbers in here to completely factor it here. X for this binomial here, we're going to have to go into complex numbers for that. So let's try one now. Write the polynomial as a product of factors that are irreducible over the rationals. So we're gonna irreduce it over rationals as a product of linear and quadratic factors that are irreducible over reals. And C in completely factored form, meaning you're going to use complexes here. You're going to use irrational numbers up here, and then you're going to use rational numbers here. You're going to use rationals here, then irrationals here. Will be the method that you use here. So when we factor this back, this fourth degree polynomial, we come up with this x squared plus, this is going to give us problems. So, and also we're going to have to go into a square root of 7. So x minus square root of 7, x plus square root of 7, x squared plus 1. So we're going to use irrational numbers here, And then down here, we're going to use complex numbers along with the irrationals. Now, the complexes are not part of the real number system, but we can go ahead and use them anyways to factor that. Okay, our next example, finding the zeros of polynomial function. We have this thing here, given that 1 plus 3i is a 0 of f. So we know 1, 0 here. Complex 0 occurrent conjugate pairs. You know that 1 minus 3i is also 0 of f. 1 plus 3i, and then 1 minus 3i would be a 0 as well. This means that both x minus 1 plus 3i and x minus 1 minus 3i are factors of f. Multiplying these two factors produces x minus 1 minus 3i, x minus 1 plus 3i. And then when we hash that out, we come with x minus 1 squared minus 9i squared. And then when we square this, 9 minus 9i squared, we know I squared is negative 1. So negative 1 times negative 9 be positive 9. And then this up here, will, when you multiply that out, will become x minus 2x plus 1. So we have x squared minus 2x plus 10. Using long division, you can divide x squared minus 2x plus 10 into f to obtain the following. So when we long divide this by the original here, x squared minus 2x plus 10 into this, we get this as our quotient up here with no remainders, so everything works fine and dandy with that as a quotient. So you have x squared minus 2x plus 10 times x squared minus x minus 6 as your two trinomials that are factors of that. And then this here can be divvied up into these two binomials. So we have that. Are we done yet? No, we're not done yet. And you can conclude that the zeros of f are 1 plus 3i, and then x equals 1 minus 3i, x equals 3, and x equals negative 2. And then you can use a graphing utility to determine that negative 2 and 3 are x-intercepts of the graph of f. You can check that on your graphing calculator with the original fourth degree polynomial. So here it is again. Negative 2 and 3 would be x-intercepts, and then we have this trinomial here as well that are again is a factor of that original fourth degree polynomial. And sure enough, here is your plot here, and then you have zeros there, x equals negative 2, and then down here x equals 3 would be an intercept. So you can check it, graphing it, and that's what you come up with for our original fourth degree polynomial. Cool, right? Let's try one now. Use the given 0 to find all zeros of the function. So here's our given 0 here, 5 plus 2i. Okay, in this problem here, use the given 0, and then here is our given 0 here in 5 plus 2i here to find all the zeros of this function here. So if we use long division here, polynomial long division, we set up 5 plus 2i as our divisor here, and then we multiply through here 5 plus 2i times this, and we get 5 plus 2i, combine like terms. Then we get to negative 2 plus 2i, multiply that by that, and we end up with negative 14 plus 6i, combine like terms. Then we get negative 15 plus 6i, multiply this by negative 15 plus 6i, and we get negative 87 for that. Combine like terms, and we get 0. So that's definitely a 0 there. And then 5 minus 2i, we do the same thing just to check it. 5 minus 2i, and we multiply that by that, and we combine like terms here. 3, these cancel out, then 5 minus 2i times 3, we get this, then they cancel out, so we come up with this here as our quotient for that with a 0 remainder, so that's a 0. The 0 of x plus 3 is x equals negative 3, So x equals -3 here. And then the zeros of f are -3, 5, plus or minus 2i. So there are 3 zeros there of this. So that is your lesson 2.5, pre-calculus math. If you have any questions, email me here. If you need worksheets or homework sheets, email me here as well. Thank you very much.